Welcome to the deep dive. We take the sources you share and really get into the core insights. It's about giving you that shortcut to being well informed.
And today we're tackling something, well, foundational in programming.
Yeah, it's about how we choose to represent data. It sounds maybe a bit basic.
But it's surprisingly powerful, isn't it? That choice really shapes the code we end up writing.
It totally does. It's like the blueprint, as you said. It dictates storage, manipulation, the whole program structure, really.
Exactly. And, the inspiration for this deep dive actually came from looking at some common Lisp tutorials.
Right, specifically ones implementing tic-tac-toe. Now, we're not trying to reinvent tic-tac-toe here, obviously.
No, but what was fascinating was just how many different ways people represented the game board.
Seriously, we saw, like, simple strings right through to bitmaps and even representing the whole board as just one number.
Which kind of begs the question, why bother with all these for tic-tac-toe? It's simple.
But that's the beauty of it, isn't it? The game's simplicity lets us see really clearly how each representation choice forces our code down different paths.
You see the trade-off starkly.
So that's the plan. We're going to walk through several of these representations. We'll see how that data choice hits things like, managing state, how you loop through the board.
Even touching on things like potential concurrency problems.
Yeah, we'll try and make it engaging, give you some of those aha moments without drowning in, super technical jargon.
Sounds good. So where should we start? Maybe with the players themselves. Seems easy enough.
Okay, yeah, so X's and O's. Some tutorials just use strings, like X and O.
Which works, of course. But in Lisp, it feels a
bit disconnected from Lisp's whole symbolic nature.
Exactly. The sources we looked at pointed out that Lisp gives you more symbolic options, kind of built in.
Like using Lisp symbols X and O or keywords X and O.
Right. Or even, getting fancy with Unicode characters, U and IL.
Okay, but why does that small choice matter?
Well, it's subtle, but using symbols or keywords feels more aligned with Lisp's philosophy. They're these atomic things, super efficient to compare.
Ah, okay. So it's less about the string of characters and more about the unique thing it represents.
Precisely. It nudges you, even at this tiny level, towards thinking in a more symbolic way, which kind of sets the stage for bigger data decisions.
Got it. So a small hint of how representation influences style. Let's move to the main event then. The game board.
The 3x3 grid.
Yeah. And the sources mentioned, like in job interviews, people almost always jumped to a two-dimensional array.
It's the obvious visual mapping, isn't it? A grid looks like a 2D array.
Makes sense. Practical for lots of things.
Totally practical. But, and this is key, especially in a language as flexible as Lisp, it's not the only practical choice.
Which brings us to the alternative. A list of lists, representing the board that way.
Right. Now, that might not feel quite as direct visually.
Not immediately, no. But the interesting part is how Lisp's list processing tools change how you write the game logic.
Completely changes it, like checking if a row is all X's. In Lisp, the every function handles that beautifully.
Oh, okay. So you pass it the row list and a check.
Yep. And checking all the rows, you use sum with every, it becomes quite elegant.
So choosing lists kind of pushes you towards a more functional style.
Definitely. You start leveraging recursion, these built-in list functions. It's a different feel from the loops you often see with arrays.
The source even showed that neat trick for transposing the board swapping rows and columns.
Oh, yeah. The apply #map list, list of lists one. It's clever.
And diagonals, no built-in. But the recursive diagonal function they showed was a good example of list thinking.
Exactly. It's all about operating on lists, often recursively. Your code structure mirrors that functional approach, less about stepping through indices.
And more about transforming lists. And apparently this list approach adapts fairly well to different board sizes too.
Yeah, often the core logic doesn't need massive changes.
Okay, but there have to be downsides, right?
Yeah.
Performance, memory.
Well, yes. The way Lisp lists all those con cells, pointers, it can be less memory efficient and potentially slower than a tightly packed array.
But the source made a good point.
That for tic-tac-toe, the difference is probably negligible. It's tiny.
Right. You gain code that aligns better with Lisp's strength, potentially. For a performance cost you won't even notice.
Exactly. The structure of your code changes, and that's often more significant here.
Okay, so lists offer a very Lispy functional flavor. Let's circle back to arrays then.
The default choice for many.
And the sources highlighted that arrays often lead to iterative code. Lots of loops, right?
Typically, yes. For loops, while loops, manually indexing through rows and columns.
Which is fine, common in lots of languages. But Common Lisp, being Lisp, offers ways to abstract that iteration, even with arrays.
It does. One I mentioned was using do macros.
Right, like the do example. You basically build your own little looping constructs.
Yeah, it lets you write code like do row, cellboard row index.
Yeah.
And it hides the actual array indexing loop. It's like a custom tool.
Makes the code using it cleaner, focused on what to do with each cell.
But, and this is an important distinction the source made, it's still fundamentally imperative. You're hiding the iteration details, but it's still a step-by-step process underneath.
Okay, so do macros abstract the loop details? What else?
A more declarative approach mentioned was the series package.
Ah, yes. This seemed really different. How does it work?
Instead of thinking about explicit loops, series lets you think about iterations as, well, as series of values, sequences.
Like a pipeline for data.
Kind of, yeah. You describe what collection of values you want, like all cells in this row, and the series macros handle how to get them.
This source showed functions like scan row, scan column, scan diagonal. These return a series.
Exactly. They return a series representing the cells in that line, and then you have functions that operate on those series.
Like E-series, to check if all elements in the series are the same.
Precisely. See how it separates things. First, you define how to get a sequence, scan a row. Then you define what to do with it, check if all equal.
That's neat. The column EQ example using scan column and E-series seemed very concise.
It decouples the iteration logic from the operation logic. Your code structure shifts from do this, then this, then this to get this sequence, then apply this transformation or check.
Okay, that makes sense. A different way to structure the thinking. Now let's throw another curveball in.
Uh-oh.
The linear array representation. One dimension instead of two.
Flattening the grid. Instead of 3 by 3, just 9 cells in a row. Cells 0 through 8.
Yeah. Seems less intuitive, maybe. How do you handle rows and columns?
Well, the source explained it's about intervals. A row, column, or diagonal becomes a set of indices with a regular stride between them.
Okay, like the middle row's index 3, then 3 plus 1 equals 4, then 4 plus 1 and 5, a stride of 1.
Right, and the first column is index 0, then 0 plus 3, 3, then 3 plus 3 equals 6, a stride of 3.
So you need a starting point, the base index, and the jump size, the stride.
Exactly, and what's cool is that the series package works beautifully here too.
Really? Even with the flat array?
Yep. The source introduced trace indices, which generates a series of these indices based on a base and stride.
Okay.
And then scan trace uses those indices to pull out the values from the linear array, giving you a series of the cells in that line.
Ah, so you can still get your series of row column diagonal cells even from the 1D array using this base and stride idea.
Precisely.
Yeah.
Which means you can still use functions like eq series on the result. The trace eq function they showed was basically eq series applied to the output of scan trace. Very neat.
So the series abstraction works across both the 2D and 1D array representations. That's quite powerful.
It really demonstrates how a good abstraction lets you maintain a consistent coding style even when the underlying data structure changes.
This is really driving home the main point, isn't it? How you represent the data fundamentally changes how you write the code to interact with it.
Absolutely. Recursion with lists, iteration with arrays, maybe hidden by macros, index math with linear arrays, different patterns emerge.
And it goes beyond just accessing data, right?
Yeah.
What about managing the game's state?
Good point. The sources linked this to the stateful versus stateless programming idea.
Stateful meaning you change data in place, like modifying an array element.
Exactly. Mutable data structures often lead to stateful programs, like that whiteboard analogy you erase and rewrite.
And the tutorials using arrays often did that implicitly, just change the array cell.
Yeah, that Cephon and Arif is the classic stateful update.
But there's a stateless alternative.
Yes, the list of moves representation mentioned in the sources.
Okay, how does that work?
Instead of a board that changes, the state is the sequence of moves made so far. To make a new move, you don't change anything. You create a new state by adding the move to the list.
Ah, like a log file. Every step creates a new version of the history.
Exactly. It's an immutable approach. Making a move returns a whole new game state. Checking for a winner means analyzing that sequence of moves.
How does that change the code structure?
Fundamentally, operations don't have side effects on shared data. They produce new values. It can often make code easier to reason about, less prone to certain bugs,
Yeah.
and easier to parallelize, maybe.
That leads right into concurrency. The sources touched on this.
Right. Mutable state, like that array you keep changing, can be tricky when multiple things try to change it at once.
The add mark.
Hmm.
example they gave just setting an array element. If two threads tried to mark the same empty spot simultaneously.
You get a race condition. Who wins? The final state depends on timing luck, basically, which is usually bad.
But the immutable approaches, like the list of moves.
Much cleaner for concurrency. Since nothing is changed in place, there's no shared mutable state to fight over. Each operation works with its own data or produces a new independent result.
So choosing an immutable representation can sidestep a lot of concurrency headaches.
It absolutely can. It's a significant structural advantage in those scenarios.
Okay, so we've covered arrays, 2D, 1D, lists.
Mm-hmm.
What else did the sources mention? Some more specialized things?
Yeah, briefly. One was bitmaps, inspired by chess engines, apparently.
How does that work?
You use two sets of bits, maybe two integers, one to track player X's positions, one for player O. A 1 bit means they occupy that square, 0 means they don't.
And the advantage?
Speed. You can use super fast bitwise operations, AND or XOR, to check for wins or make moves, potentially very efficient.
Interesting. And the other one? Using a single number, a fixed num.
Right, representing the entire board state as one integer.
How is that even possible?
Well, tic-tac-toe has a finite and actually quite small number of possible valid board layouts. You can assign a unique integer to each possible state.
Whoa. Okay, so how do you play?
Often you'd use pre-computed lookup tables. Given the integer for the current state on a move, the table tells you the integer for the next state. Same for checking wins.
That sounds potentially extremely fast.
Probably the fastest and most memory efficient if done right, especially if memory is tight.
So these examples, the bitmap and the fixnum, really show that the obvious 2D array isn't always the ultimate answer.
Not at all. The best choice really depends on what you're optimizing for. Simplicity, immutability for concurrency, raw speed, memory usage.
It comes back to what the sources were emphasizing. Programming is about abstraction.
And choosing your data representation is one of the most fundamental abstractions you make. It ripples through everything else.
Good programmers, then, are making informed choices here, not just defaulting to the first thing that looks like the problem.
Exactly. Thinking about the trade-offs. The sources suggested maybe thinking about the operations you need, first check win, make move, find available spots before locking into a specific data structure like an array.
Does that help choose?
It can guide you. Maybe you realize you need easy immutability, pointing towards lists or functional approaches. Or maybe raw speed is paramount, suggesting bitmaps or fixnums.
And the source mentioned using things like generic functions or CLOS objects in Lisp to abstract over the implementation.
Yeah, so you could define a generic make-move function and have different methods for the array version, the list version, etc. Lets you swap implementations more easily.
Okay, let's try and wrap this up. What's the big takeaway from this deep dive?
I think it's just how profoundly that initial choice of data representation impacts, well, everything about the code that follows.
Yeah, the structure, how you handle state, how you iterate, even how you deal with concurrency. Tic-tac-toe, simple as it is, showed that really clearly.
It's a fantastic microcosm of these bigger programming concerns.
So the provocative thought for our listeners.
Maybe it's this. When you start your next project, are you just grabbing the most obvious data structure off the shelf?
Or could you take a moment? Think about alternatives. Could a less obvious representation actually lead to a cleaner, more robust, maybe more performant solution for your specific needs?
Needs around state, concurrency, future changes. Sometimes the slightly less direct path is actually better engineering.
And for anyone wanting to really cement this, the sources had that homework, right?
Yeah. Try to invent another way to represent the tic-tac-toe board. There are still others we didn't cover.
And then try implementing the available moves function for all the different representations we've discussed today: arrays, lists, linear arrays.
It's a great exercise to feel the differences in the code structure that each representation encourages.
Absolutely. Well, that was a fascinating look at something seemingly simple with surprisingly deep implications. Thanks for joining us for this deep dive.